So in our last class, we discussed about prime ideals, maximal ideals, and their relations. Then we talked about prime element as well as irreducible elements and their relations. So these relations and the relation on the properties of prime ideals and maximal ideals are very important because in from competitive exam viewpoint, every year you will find many of these questions. They usually these questions are being asked from this particular part, from maybe NET, GATE, NVH, MTIF, or everywhere. Today we are also doing the same thing, but for a particular ring. So we are basically dealing with some polynomial ring Rx, and this polynomial ring plays an important role. So suppose we assume that R is a commutative ring with 1, so we will deal with Rx. So this is a polynomial ring, polynomial ring over R, over the ring R. So here, so since R is a commutative ring with 1, so of course Rx is also a commutative ring with 1. So here we assume that R is a commutative ring with 1. So as a result, Rx is also a commutative ring with 1. So as I mentioned in my last two classes, that in my definition of prime ideals or prime elements, maximal ideals or irreducible elements, we assume that the ring R to be a commutative ring with 1. Note that I must say that you can do it for any arbitrary on over any arbitrary ring with or without having identity element, but for the sake of simplicity we assume that R to be a commutative ring with 1. So in this class as well, we assume throughout that the R is a commutative ring with 1. So since Rx is a polynomial ring, Rx is also a commutative ring with 1. Okay. Now a few more properties we need to explore. Okay. So before going to that, let us have some problem from competitive exam. Let us try to solve this problem maybe. Okay. It came in June 2019. So here it's a particular kind of polynomial ring. So it's over Zx. So Z is the set of all integers. So it says that let Zx be the ring of polynomials over integer. Then the additive group Zx is, so the options are isomorphic to the multiplicative group Q plus of all positive rational numbers, isomorphic to the group of rational numbers Q under addition, countable, uncountable. So which one would you like to answer? Okay, so there are four options. It may be a multiple correct choice option. That means more than one option could be correct. So tell me, which one you would think that would be appropriate, and of course why. So first let us try to give. So no clarification at this point of time. I want just number 1, 2, 3, 4, or combination of this 1, 2, 3, 4. So somebody please try.
Sir, option 1.
Option 1. Okay, somebody says option 1.
Option 1 and 3.
Somebody says option 3 or 1 and 3.
Sir, both 1 and 3.
Okay, so both 1 and 3. Somebody says the answer would be 1 and 3. Let's see. So answer is 1 and 3. So anybody else having some different answer? Anybody else having some different answer? Okay, so can you please tell me why this is 1? One says that this is isomorphic to the multiplicative group Q plus of positive rational numbers. Can you please explain how the isomorphism would be defined from where to where?
So we first start with an enumeration of the primes.
Okay. So if you go back to this problem, it says that Zx. So somehow you have to make an isomorphism from Zx to Q plus. That means the set of all positive rational numbers with respect to, of course, multiplication. So for that, as we know that what is a rational number? Rational number must be of this form, some a by b, where a, b are integers and b not equal to 0. And of course, for unique representation, this a, b must be relatively prime. Okay, so that's the definition of a rational number. That means both a and b, they are from Z. And we know that the building block for Z, so from the fundamental theorem of arithmetic, we know that any integer, say greater than 1, can be expressed uniquely as a product of primes. So P1 alpha on any n can be represented in this form, Pk alpha k, where each of Pi's are distinct primes. Okay. So since we have this fundamental theorem of arithmetic at our hand, so every integer can be written, which is greater than 1, can be written uniquely in this form. So in case of this is say from Z, so we can think this as some, maybe we can make some minus before that and something. So we can think of both of them are positive, and we can arrange something like this. Now, Aniket, can you please continue your argument that why you are first making this enumeration?
Yes, sir. So the idea of the enumeration is to help us later on in substituting the various primes for the powers of x.
Okay, good. So what
So
he does, first step, what he made, he first made an enumeration of the primes. So what does it mean? Means you know that the prime numbers are countable, so you can certainly enumerate them. So you know that who are the first prime, who are the second prime. So like this. So suppose this is my first prime, this is my second prime, third prime, and so on. That means you know that this value is 2, this value is 3, this value is 5, and so on. So you first enumerate all of them. That means you just write it down one after another in this particular fashion. Okay,
then we define a homomorphism phi
okay,
from the polynomial ring to the positive rationals,
yes,
and we define it as summation a and bn, this polynomial,
summation.
summation a sub n x to the n. I mean, sorry, sir.
Okay, so xi, this one, right? I equal to
Yes,
say 0 to n.
this is defined as product of p sub I to the power of a sub I,
Power of,
a sub I
okay, yes,
over I.
1 to n. Okay. So see, so you now know what is say P0. If it starts from say, I may start it from P0 maybe. So maybe it's just an enumeration. So I can put it P0, P1, P2, and so on. So like this. So you know what is your P0, you know what is your P1, and so on. So suppose, for example, suppose you have say 5 plus 3x plus 9x square. Okay. Now, so phi of this, what will be this value according to this definition? Could you please tell me what would be this value? So this is your A0, this is your A1, and this is your A2. So this will be product of, so A0, A0, for A0 you will have P0. So P0 to the power A0 into P1 to the power A1, and then P2 to the power A2. So you know what is P0? P0 is 2. So it's a product of, it's not a product, it's already in a product form. So P0 is your 2 to the power A0. A0 is your 5 into P1 is your 3 to the power 3, and then P2 is your 5, then it's your 9. So that is the meaning of this function phi of this. Okay. So he defines a function. So it's no doubt that all of them are positive real number. Now what happens if you have something like negative? So here you had, say I had, instead of 9 I might have minus 9. Okay, then it's simply minus of this, but that means 1 by 5 to the power 9. So it's nothing but 2 to the power 5 into 3 cube into 1 by 5 to the power 9. See, in any case, it will not go out of positive rational numbers. So now this is a positive rational number, this is positive, and product of them. So there is no doubt that, okay, it's take any polynomial that will ultimately mapped into a, a positive rational number. Okay, so that part is clear. So the function is fine. Now what you need to show? First, we need to show phi is a homomorphism. Then we need to show phi is a bijection. And if we are able to do so, then that will be your conclusion. Phi is an isomorphism. Okay. So now, can somebody else will able to tell me why this is homomorphism? Why this
Actually,
is homomorphism?
we can check the homomorphism quite easily if we take arbitrary element a0 plus a1x plus a2x squared plus
So
ax
summation
to the
is
power n.
fine. How, what's about product? How to check the product? Yes, I mean that's not difficult, I must say, but how to check the product? For example, suppose you have phi of, I am just doing for a, I mean for a simple case, say a0 plus a1x. That should not be the general proof, of course. X square and the product of, say, b0 plus b1x. Okay. Then how will you define this one? Okay, so that you need to check, and if you check this, then you will find that once you do this, then you will able to understand how the general case will be happening, and you can write it in terms of in a compact form, and then you will be able to prove that this is nothing but a homomorphism. So I'm not going to do that. To convince yourself, just try to do some simple expression of like this form, and then make a product, automatic product, and then check whether that really matches with this kind of definition or not. Then you will be convinced how for the general one you will find it. And the onto is also very easy. Take any positive real number, then you can, by using the fundamental theorem of arithmetic, say AB belongs to positive real number, then by fundamental theorem of arithmetic you can express A and B separately, and then if A might have some common prime with B, then you can adjust them on the power, then that would be ultimately written in terms of power to some integer, and then depending on this integers, maybe positive or negative, you can find some polynomial whose map will be this A by B, and so that would be an onto mapping. So as a result, you can see that Zx is isomorphic to Q plus. So now, I mean, intuitively, you may not be able to guess that, okay, how the polynomial ring may be, especially this Zx is isomorphic to Q plus, but it's quite a surprising kind of result that it's really correct. Okay. Now the second option. So you gave 1 and 3 to be correct. Now, why the second option is not correct? Why the second option is not correct? Anybody?
Sir, we already know that Q plus and Q are not isomorphic as groups.
Okay, why not? That's correct. Why not?
Sir, any finitely generated group in Q under addition is cyclic, but this is not true for Q plus.
Okay, yes, but yeah, that's true. You can also argue like in Q
1
plus,
minus
what is the order of minus one? Okay, minus one is not there. Okay, so in Q plus, minus one is certainly not there. What you are talking about? Yes, whatever justification you gave was correct. Uh, Anybody else? Any other
minus
justification?
1 have the order 2. Minus 1
In
have the
in
order
Q plus,
2.
minus one is not there. It's positive rational number.
Q plus, not Q under addition. Q plus
O-
and Q under addition. Oh, okay, 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 okay.
Okay,
Still, I can do it. Phi x, if I take any arbitrary element phi x, then there must be some image for that too. Say so phi x by 2 plus x by 2, that will become up in image phi x by 2 square.
okay,
That will
yes,
be
yeah. So
result to
square
root
root
2.
something.
X by 2 is x by 2 is rational, but root 2 isn't rational.
Yes,
That's
yes,
it.
good. Okay. Uh, then 3 is of course true because you can check with Q plus, and of course if it is countable it cannot be uncountable. So 1 and 3 are the correct options. Is it clear to all of you? Any question or doubt anybody has, please? Anybody? Is it clear to all of you? Okay, good. Okay, so now we will go for a few more results. So today I'm going to give you many such results. But before that, let me do few things. Like, what do you mean by? In my last class, I have already explained about units of a ring. I have already talked about what do you mean by associate, associates maybe, associate of a non-zero element A belongs to R. What do you mean by? That means, say B is said to be an associate of a non-zero element A belongs to R if there exists some unit U belongs to R such that A equal to UB or something like this. Okay. So an element B belongs to R, which has to be a non-zero element, is said to be an associate of A if there exists some unit in R such that A equal to BU. For example, 2 and minus 2 are associates in Z. Okay. Again, say in I and plus 1 and minus 1, are they associates in Zi? Are they associates in Zi? Of course, because you can write like this 1, then you if I multiply like this. So in Zi, in my last class, I have already shown you who are the units. Then 1 minus 1 plus minus I are the units of Zi. As a result, so this is unit. So if I multiply with I square, this minus 1, and so this is minus I square, that means plus 1. So I minus plus minus I, for example, 2 and 2I, they are units, they are associates in Zi and so on. So now you know what do you mean by units of a ring. So of course, in my, as I mentioned in my whole class, I assume that the ring is with commutative ring with 1. Okay. So now we are going to define a very interesting topic that is known as factorization. So we all know what do you mean by factorization. So in our last class, we already talked about irreducible elements. So what does it mean? So a non-zero non-unit element, say A belongs to R, is said to be an irreducible element in a commutative ring with 1 if A equal to say PQ for all PQ belongs to R implies either P is a unit or Q is a unit. Okay, so A has to be non-zero non-unit, and if for all PQ, this may not be for only one, so it has to be true for all PQ belongs to R. So based on this irreducible elements, associates, and so on, we are actually going to define a term called factorization. So factorization of an element, factorization of an element A belongs to R. Now, suppose I say that in Z, for example, in Z, can you factor 0? What is the factorization of 0? What is the, suppose I don't know anything about factorization of ring, I just asking you a simple question. What is the factorization of 0? Anybody?
A dot 0 for all A belong to Z.
What?
A dot 0 for all A belong to Z.
A dot 0. Okay, so what do you say that is a factorization? So it's a factorization of 0 like this. So the question is, what do you mean by factorization intuitively? First, let us finalize what do you mean by a factorization intuitively. So have you ever tried to factor 0? Or what is the factor of 1? What is the factorization of 1? And then what is the
1 in Z,
factorization of, yes, 1 in Z?
1 equal to 1 into how many times? 100, whatever it may be.
What? 1 equal to 1 into 100.
1 into 100 times, 1 to the power 100, we may say.
Okay,
Or 1 to the power 100, anything.
okay. And then what is the factorization of 4?
2.2
Anything else?
into 1 to the power 100 or whatever.
So 2.2 into, sorry, 1 to the power 100. It is also a factorization. Okay. So now tell me, what do you mean by a factorization intuitively? Suppose I have no idea about what do you mean by the factorization of some element in a ring. Suppose I don't have, I actually want to uh, make a kind of idea what should be the definition. So it should come intuitively. So now tell me, so you have given lots of example. Now tell me your definition of factorization with.
To avoid this confusion, identity shouldn't be there because it has too many representations.
Okay. No, now you know. So you with something, some logic is at your back end, and based on your logic, you have given such kind of factorization within Z. Now, based on that logic, try to define what do you mean by factorization of an element. Is the question
There
clear?
shouldn't be the identity element.
Sorry, where there should not be in. Okay. So what you did was, okay, some logic you have made it. But you can understand that here you will have many kinds of different factorization options. For 4, you might have 2 into minus 2, sorry, minus 2 into minus 2, as well as this many options. So do you really think that in your factorization definition, this kind of expression should be there? What would be your opinion? In your factorization
No,
definition, shall we allow this kind of things? Anybody?
no.
So we should not allow this kind of thing. So what is the speciality of this and this? What is the difference between this and this and this? So here you are basically allowing something which is a unit. So you are multiplying it with the identity element. So that should not be there in your uh, definition of the factorization. But here you are convinced that they are correct. Okay. So they are not unit, of course. Then I have two different factorizations of 4. So one is 2 into 2 and minus 2 into minus 2. So both of them are 4. And according to your intuitive idea, both of them are valid. Of course, they are valid. Then what should be the factorization of 1? So you can understand that this factorization of 1 has some ambiguity. So it may be 100, 1000, 1 lakh, doesn't matter. Similarly, for 0, you can put any a here if you make it like this. So these two has some ambiguity. So it's better to remove this from your definition to become a factorization or to become a part of the factorization. And also you have removed something which are units or which are the identity element of this uh, from this expression. So what are left basically? So you are left with not considering the zero element as well as the unit element, and also you are dealing with, in case of integers, you are dealing with prime elements, but they are not actually prime integers. But in Z, in my last class, I have already shown you they are prime elements. Now, if you consider this to be a prime elements, then we have seen that not always that a prime element be the irreducible element. Okay, but in case of Z, since the Z is a PID, we have already seen in your last class that in PID, prime element and irreducible elements are basically the same. But there are situations, in my last class I have already given you some examples where we have shown that the prime element and the irreducible elements may not be the same. So if you go back to your last class, then what should be the definition? So the factorization definition, you can explain like this. So here we are actually considering not only commutative ring with 1, but actually we are going towards factorization domain. So we assume that we are going to do factorization in an integral domain. So let D be an integral domain, a non-zero non-unit element A of D is said to be is said to not be okay is said to have a factorization if A can be expressed as A equal to A1, A2, AN, where AIs are irreducible elements of D. This expression, say this expression A0, AN is said to be a factorization of A in D. Okay, so now it's clear. So we are actually going towards factorization domain. That's why I started with integral domain. So actually I am looking forward, what do you mean by uh, factorization of an element in an integral domain. So first you see that I have already discarded non-zero and non-unit. That means you cannot factor for zero element or unit elements. Okay, is said to be a factorization if this can be A can be expressed as a product of irreducible elements. See here n is there, that means you have to make it a finite product of elements of n. So that means element of D. It should be a product finite number of product of elements of D, and each of these element must be irreducible elements. Now you can understand that what should be this. So this 2 into 2 and also minus 2 into minus 2. Now you may think of that they are two different factorizations, but you can understand very well that 2 and minus 2 are associates. 2 and minus 2 are associates. For example, if I have 6, I can write it in terms of 2 into 3, but I can also write in minus 3 into minus 2. So you may have that, okay, we have two different factorizations, but frankly speaking, they are not, because here, though we have used minus 2, but suddenly 2 and minus 2 are associates. Here 3 and minus 3 are associates. So they cannot be considered as two different factorizations. So is the concept clear to all of you? So now the question is, what is a factorization domain? So what is a factorization domain? So till now what we have discussed is the definition of factorization. Now what is a factorization domain? So now you can understand that if every non-zero non-unit element of that integral domain has factorization in D, then we call that integral domain as a factorization domain. So what is the definition of factorization domain? So let D be an integral domain if every non-zero and non-unit and non-unit element of D has a factorization in D, then we call D as a factorization domain. Okay, so example, Z is an example of a factorization domain. Z root 5I is again an example of a factorization domain. But we must pay some extra attention on Z root 5I. So the first question that comes to your mind, that can you give an example which is not a factorization domain? So first question, give me an example of an integral domain which is not a factorization domain. It's quite interesting. And so this is your first question. So I give it to you as homework. So please check it. And in my next class, just or maybe in the assignment or somewhere, I will ask you this question. Okay, not now. So please, those who know this answer, please uh, give the chance for others to think or at least to search so that they can also get the answer. Okay, now why I'm telling that Z root 5I has some special property. So of course, this is an example of a factorization domain. Of course, this is a FT, but it has some special property. For example, suppose I take 6. If I take 6, then 6 can be written as, of course, 3, 2, or minus 3, minus 2, or minus 2, 3, or -2, -3, or there may be two more options, 1 plus root 5i, 1 minus root 5i, or you can put 1 minus root 5i first and then 1 plus root 5i. Okay. Now you can see that all this, they are basically having the associate structure 2 minus 3, sorry, 2 minus 2 or 2, 2. They have some associate structures. But question is whether 3 is associated with any of them, whether 3 is or 2 is associated with any of them. In my last class, I have already discussed that, of course, they are not associates. So it can be proved easily that they are not associates. That means for 6, I will have at least two types of factorizations. Say 1 plus root 5i. So these two, they are not associates form. So at least two factorization of 6 in z root 5i. That means the factorization form is not unique. So now you understand what do you mean by unique. So if I have this, then we call it this is unique. So this and this may look different, but since they are associates with each other, we do not consider as to be different factorization. But if they are not associates, then suddenly we'll consider these two factorizations as two different factorizations. As a result, we can certainly say that this factorization of 6 is not unique in, so not unique in z root 5i. So now you understand that there could be a notion of unique factorization domain. So what do you mean by UFD? That is unique factorization domain. And now you can understand what do you mean by the unique. So how the uniqueness is defined. So uniqueness is defined in terms of the associates and the units. So now you understand what do you mean by unique factorization domain. Okay, so if I write it formally, then I can write in that way. So of course, unique factorization domains means it has to be a factorization domain in which every non-zero and non-unit element will have unique factorization. So let us try to define more formally. So an integral domain, so and integral domain D is called an unique factorization domain, unique factorization domain. In short, we call it UFD if the following two conditions are satisfied. The following two conditions, two conditions are satisfied. So what are the conditions? Condition 1, it says that every non-zero non-unit element A of D can be expressed as, that means to justify the FD property. So every non-zero non-unit element A of D can be expressed as A equal to say A1, A2, AN, where each AIs are irreducible elements of D, are irreducible elements of D. So that part is already there because it's a factorization domain. And now the second property is basically to highlight how to define formally. This definition is quite interesting because you can make people understand easily by giving some example. But when I say something very formal, then it's not always very easy to write the formal way. So writing formal way is an art. So you must capture that art. So you must read. That's why you should read books. Otherwise, unless you read some formal proofs, it would be very difficult for you to develop the writing, how to write this formal way. So that's a developing. To develop a formal way writing, you must read some of the textbook. Otherwise, it would be very difficult for you to develop that writing style. So if it says that if a equal to say a1, a2, an, and a equal to b1, b2, bm, be two factorizations, be two factorizations of a, then so what do you mean by factorization of a? As a product of where each bi and ais are irreducible element, then the first thing it should satisfy, n should be equal to m. N should be equal to m, and second property it should satisfy, and there is a permutation, there is a permutation sigma on the number of elements 1 to n. Now you can see that n and m are same. So 1 to n and 1 to m, these sets are same. So there is a permutation sigma on this such that ai and b sigma I are associates in D for all I 1 to n. Now try to think, what do you mean by this? So suppose I have two different, for example, in say in Z for 6 I have two different I say minus 3 minus 2. I have two different factorization of 6 in say Z. Then you can see that the number, so here n and m are both 2. So both n equal to m equal to 2. So how many permutations are there on two elements? 2 factorial, that means two permutations are there. So what it says that so this is my a1, a2, and this is my b1, b2. So what it says, so a1 must be equal to what? What not equal? So a1 and b, a1 and b2. What is b2? B of sigma of 1. Why this is 2 means I have the permutation sigma. So let me write it in a better way. Say for example, okay, let me do it for little bigger number. Okay, so so I know that this is my say 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 I have 2 into 3 into say 5, that means 30. 2 into 3 into 5. I could also have minus 5 into minus 3 into 2. Okay, so here n equal to m equal to 3. So my set is 1, 2, 3, and sigma is a permutation on this 1, 2, 3. Okay. Now there are total 6 many such permutations. So suppose I assume that my permutation is like this, sigma say 1, 2, 3. So 1 goes to, so here 1 goes to 3, 3 goes to, so it's there, 2 goes to 2, and 5 here, that means 1. Suppose this is my permutation. That means sigma of 1 equal to 3, sigma of 2 equal to 2, and sigma of 3 equal to 1. Okay. So this is my A1, A2, A3, and this is my B1, B2, B3. What it says that A1 and there exists some permutation sigma such that A1 and B sigma 1 must be associates. Eto and eto are associates. Why? What is B of sigma 1? B of sigma 1 is B of 3. That means A1 and B3 are associate. So see, A1 and B3 are associate. Similarly, A2 and B sigma 2. What is B sigma 2? Equal to B2, because sigma 2 is 2. See, they are associate. And similarly, A3 and B sigma 3. What is B sigma 3? That is B1. So A3 and B1 are associate. Okay. So that's the way how it could be written in a formal way, because when we explain it, we just give some example that is very easy to write or too easy to make people understand. But sometimes when you are writing it, it may not be that easy. So here, by using this concept of permutation, we can explain it quite easily. So just have a look at once again the definition here for the second one, for the unique one. So if A equal to A1, A2, An, and A equal to B1, B2, Bm be two factorizations of A, then first property is n must be equal to n. That means they should have same number of irreducible elements. And then there is a permutation sigma on n elements such that ai and b sigma I are associates in D. That's all. Okay. So in that way, what we can say that Z is a unique factorization domain, but Z root 5I is not a unique factorization domain. Is it clear? Okay. So I will come to this properties of few important things are there. I am not considering it now, but of course they are very important. So I will come to them maybe later on. But before that, I will just use the term unique factorization domain and all, and then I will use it this as a term, not as their properties, but as their term. I will use it and I will do few of the problems that are useful for NET exam. So now I am going to give you very interesting properties, and you will be surprised to know that if you know these properties quite well, or if you remember these properties quite well, then you will certainly be able to do almost all the problems that are usually asked here in NET or GATE exam or even NBHM exam related to this irreducibility of polynomials. Okay. So till now we have already mentioned about irreducible elements. So since Rx is a polynomial ring, so there must be some polynomial which are irreducible, and these polynomials are called irreducible polynomials. So very frequently in many questions it has been asked that whether a given polynomial is irreducible or not. Let us have a look at few of these problems and then we will do at the end. So for example, it came in 2018 net. So it came in 2014 net. It came in 2013 December net. So every year you will find at least one question from this part. So I just consider only three. There are plenty of more. I'm not considering it now. So you can do it on your own. But to do those problems, you need to have some theories. And I'm just going to give you the details of these theories, but not giving the proof. All the theorems that I'm stating here must have a proof, and it's your duty to learn the proofs from any book, any standard book. Okay, but I am giving you only the statement of the theories, but you have to take the proof from, because in this class I am not going to give the proof of those results, only the statements which will be useful for solving your problems. Okay, so first let us have a look at what do you mean by the content of a polynomial. Okay, so what do you mean by a content of a polynomial? So we are actually dealing with Rx. So here R is a polynomial ring. R is a commutative ring with 1. So R is a commutative ring with 1. So as a result, Rx is also a commutative ring with 1. Okay. So let us first consider, let fx equal to a0 plus a1x dot dot a n x to the power n belongs to Rx. So it's a polynomial. Okay. So consider the GCD of, let G equal to the GCD of the coefficients a0, a1 up to an. Now the question is, what do you mean by the GCD of the elements a0 up to an? Okay. So we know the definition of GCD within the integer set. Okay, but what could be the GCD of arbitrary ring? So in our last class we have already mentioned about what is the meaning of division. So what do you mean by an element C divides D in a ring R? Okay, that we already know. And if you have the concept of division in a ring, then suddenly you will have the concept of greatest common divisor. So if G is the greatest common divisor of this, that what does it mean? That means G divides AI for all I equal to 1 to n, and if say D is any common divisor of any common divisor of A0 up to an, then what would be your conclusion? Then who will divide whom? Then who will divide whom? So who is going to divide whom? Anybody? Anybody? Then who is going to divide whom? Then of course D is going to divide G. That's why G is the maximum out of which. Okay. So if this happens, then we call G as the greatest common divisor of A0 to AN. Okay. Now, what is the meaning of content of a polynomial? Content of a polynomial. Polynomial fx, which was given to be a0 plus an x to the power n, belongs to Rx. So the content of the polynomial ato is nothing but the GCD of a0 an. That means the content of this polynomial means the GCD of a0 a1 dot dot an. Next, the important term is, what is the primitive polynomial? What do you mean by primitive polynomial? Primitive polynomial. If content fx is a unit in R, then we call fx as a primitive polynomial. Okay, so now it's clear. So two terms are important here. What is do you mean by the content of a polynomial, and then the what do you mean by the primitive polynomial? Okay. Next, what do you mean by the quotient field? Already I have explained. I am just again giving you this idea. Quotient field of a ring R. So it's nothing but the smallest field smallest field containing R is the smallest field containing R. So of course, if you consider any ring, then it may not happen. So mostly here we are considering at the beginning, we have considering here R to be an integral domain. So we start with an integral domain because in one of the classes I have already mentioned that embedding. So suppose you have a ring here R and you want to find which is the smallest field containing that ring. Okay, for example, if R is Z, then the smallest field containing R or Z is basically Q. But if you start with some say zero divisor, for example, if we start with some zero divisor, for example Z6, will you be able to will you be able to find any field which contains Z6? Because if you find any such field, then that field will suddenly contain zero divisors. So the result is any integral domain can be embedded, any integral domain can be embedded in a field. That's very important result. So as a result, what you can think of, so as I have started with R to be an integral domain. So this integral domain, so it's a not only ring, so it should be integral domain. The smallest field containing R is called the content of the ring R. So what is the smallest field? So usually we denote it by Q. So Q of Z is nothing but the rational field. So what would be the Q of R? If I ask you this question, what would be Q of R? The smallest field containing R is R itself. Okay, and so on. So that is the idea of quotient field of a ring, of course, of an integral domain. Then I come to few of the very important results. So what we are interested in? We are interested in to find whether a polynomial in Rx, whether this polynomial is irreducible or not. Is fx irreducible? That means we need to consider few of the polynomials from that ring where this is an integral domain, and we need to check whether this polynomial is irreducible or not. Okay. To check that, there is this problem, this result is very important. So this is very important result, and you must have a look at the proof of this result from any book. It says that let R be a UFD. Now you understand what do you mean by UFD, unique factorization domain. Let fx be a non-constant primitive polynomial, non-constant primitive polynomial. Now you know what do you mean by primitive polynomial. That means take any polynomial, take their coefficients, make the GCD. If the GCD is a unit, if the GCD is a unit, then we call unit, means multiplicative inverse. If the multiplicative inverse of the GCD exists, that means if the content means GCD of all the coefficients, if that is unit, we call it as a primitive polynomial. So if is a non-constant primitive polynomial, let fx be a non-constant primitive polynomial in Rx, then fx is irreducible in Rx if and only if, this is very important, this very strong result, it is irreducible in QRX. What it says, it's very interesting result. It says that if some non-constant primitive polynomial, suppose fx equal to say a0 plus a1 x. So it's not certainly if a0 not equal to, if sorry, a1 not equal to 0, then suddenly this is a non-constant polynomial. And if GCD of a0 and a1 equal to 1, say is unit, say equal to 1, then suddenly then fx is a primitive polynomial, because say this is 1 means it's a has an multiplicative inverse, so it's an unit. So then fx is a non-constant primitive polynomial. And say here qrx, qr is the quotient field of R. What it says that if fx is irreducible in Rx, then suddenly it will also be irreducible in QRX, and the vice versa. If it is irreducible in QRX, then it will also be irreducible in Rx. So that's very important, and many of the problems we are going to use this result. Okay, if I ask you this question, suppose I have an 1-degree polynomial in say Zx, say in Zx, say consider fx equal to 4x plus 4. Okay, is fx irreducible in Zx? So what do you mean by irreducibility? Intuitively you can think of, you can factor it in terms of irreducible elements. Okay, what would be your result? True or false? Is it true or false? Somebody?
We can write for
So we can break it x plus 1. Now you can write it. So you can factor it. So this is reducible. So answer will be false. Now if I ask you the same question, is is fx equal to 4x plus 4 is irreducible over quotient field of zx, that is qx. What will be your answer? True or false? What will be your answer? True or false? Okay, Kailash, can you help us? Aniket, so are you all there? Bhaskar, can you listen to me?
টু হবে।
Okay, yes, it would be true, right? So true will be the answer. Why? Because you can write it like this again in the same form. But here, mind that in Q, 4 is a unit. So mind that in case of irreducibility of polynomials, you basically do not consider unit. If you have some unit, it's sufficient to ignore that. So you just make a common of these units, take it out, and just concentrate on the remaining part. That means we only consider on the remaining part of, if I remove the unit part, and try to consider whether this one is irreducible in QX or not. What is your guess? Can you further break x plus I into some irreducible factors of having the elements from Q? Certainly not. So this is a 1-degree polynomial. You cannot further reduce it here. Okay, that means this is an irreducible element. Is that part clear? If this part is clear, then you will be it would be easier for you to go further. Okay, so now tell me, what is, if I consider say x square plus 1, my fx is x square plus 1 in zx. This is reducible or irreducible? Which one is correct? I or R? This is,
irreducible.
yes. You can roughly understand. I will give you the much better logic why this is irreducible, but you can roughly understand that you cannot break further into a linear product like x plus something into x plus something to have x square plus 1 in zx. So suddenly this is irreducible. Now if I ask you the same question in Rx, whether this is reducible or irreducible, I or R? Nikita, it is I or R?
I.
Yes, this is irreducible. You cannot have. I will give you much better logic why it is irreducible, but intuitively you can very well think. Now, if I consider this to be in Cx and ask you the same question, it is reducible or irreducible? What would be your answer? Somebody?
আর
Yes. So this is reducible because you can reduce this in terms of x plus I into x minus I. And this belongs to Cx and this is also belongs to Cx, right? So now you can understand that this is very much depends whether on which set you are in. If you are in Z or R, the same polynomial may behave differently. That's very important. Okay, but here you can see that the same polynomial behaving differently if this is in Cx. So when we ask you the question without giving a ring, then the question must be incomplete. For example, if I ask you this question, tell me whether x square plus 1 is irreducible or reducible. The answer must be incomplete, because unless you mention about the over the ring, it's not possible for you to give you the answer. So it must be over some ring. Unless you state that, the information is incomplete, as a result you won't be able to give the answer properly. Okay, so now you can understand that if f is a field, then of course the polynomial, one degree polynomial must be a, so one degree polynomial over a field, what it would be? Suppose question is, suppose let fx equal to a0 plus a1x with a1 not equal to 0 in some field x fx. So f is a field. Okay, so question, is fx reducible or irreducible? Reducible or irreducible? Which one will be your answer? Can you further break it? You can break at most like this: a1 into x plus a1 inverse a0, right? At most that you can do. But then this is non-zero, so this is unit. So you do not need to worry about this part, only concentrate on this part. Now will you be able to further break this? You won't be in fx. As a result, this is irreducible. So any one degree polynomial over fx is, where f is a field, is irreducible. Okay, so now I come to this next result, which is very important. This result says that, so what I am telling, every one degree polynomial over f is irreducible, right? Okay, so next question is, what's about 2 degree, 3 degree, and so on? This result will be very helpful in solving many of the problems in competitive exam. The next result, what I say, let fx belongs to fx. So this is suppose a field, be a polynomial of degree 2 or 3. This is very important. This result is true only for degree 2 or 3 over the field f. Then fx is irreducible over f if and only if fx has no root in f. It says that fx is irreducible over f if and only if fx has no root in f. Mind that this result is true only for degree 2 or 3. You cannot apply the same result for if and only if case if it is of degree more than 3. Okay, so what is the meaning of that? If you have any polynomial, for example, I have just shown you the polynomial like fx equal to x square plus 1, say, over zx. Now you can understand this is a 2-degree polynomial. This is irreducible if and only if fx has no root in z. Okay, if you have, say, qx, so since f is not filled, you cannot directly use it, but okay, but you can use it in qx. Q is a field. This is a degree 2 polynomial, and since there is no root of this polynomial in q, you can directly say that this is irreducible in qx. Again, have a look at this. So this coefficient is 1, this coefficient is 1. So this is a primitive polynomial in qx. Just now I have mentioned if you have irreducible polynomial in qx, then suddenly it will also be irreducible in zx, because q is the primitive q is the quotient field of z. Just now I have mentioned this result. So here is the result where uh, yes, this one. Okay, if and only if it is irreducible. So it is irreducible in qx and the non-constant primitive polynomial, so it must be irreducible in rx. So r must be my z. So you can conclude. So this is a very powerful result. Sometimes we convert the result into q, that means set of all rational numbers, and if this the primitive polynomial is there, then we can very easily conclude the same thing over z as well. So this is very important. Okay, the next result, and mind that this is only true for 2 and 3 degree polynomial, not for more degree polynomials. Okay, now the question is what will happen for the degree, for the polynomials of degree more than 3? That would be a question. And for that, the theorem that helps us most is known as Eigenstein theorem. So Eigenstein theorem. So Eisenstein's theorem. So Eigenstein irreducibility criteria. Ability criteria. What it says, it's very important and very easy to remember, but you need to check the proof of this theorem from the book. That you must do. It says that let D be a UFD. Now you know what do you mean by UFD, and QD be its quotient field. Let fx equal to a0 plus a1x plus an x to the power n be a non-constant polynomial. Non-constant polynomial in dx. Suppose D contains a prime element P such that these conditions are very important. 1. P divides AI for all I equal to 0, 1, 2, n minus 1. Mind that this is the degree n, but it divides up to all the coefficients starting from a0, a1 to a n minus 1. Okay, so the first property says P must divide all the coefficients except for a nth coefficients. Okay, then second property, P does not divide a n. Mind that that is the highest coefficients, highest term with the highest degree term, the coefficient of the highest degree term a n, and P square does not divide a0. So P divide a0, but P square does not divide a0. Then if all these things happened, then f is an irreducible polynomial, then fx is an irreducible polynomial in, that is very important, in q dx. Now I started with the polynomial in dx, but my conclusion will be in the quotient field of d, that means q dx. Now you can understand if fx is a primitive polynomial in q dx, then suddenly you can also conclude the same thing in case of dx. So that can be done. So let us try to have a problem solving kind of thing. So let fx equal to, say, x to the power 5 plus, say, 15x cube plus 10x square plus 5x plus, say, 5. So belongs to zx. Now this, you can understand that this is a polynomial in zx and his degree is more than 3, and you really not very easily can factor this just by inspection. So you need to check whether this can be factored, or maybe by using some other tricks you can be able to find that. So the question is whether this polynomial is irreducible. My question is fx irreducible or reducible? Irreducible or reducible? So that's my question. Okay. So what would be your solution? Somebody? Somebody?
Maybe we will take the prime number 5 because that is the GCD of the middle one. Uh, so 5 divides all the things, and
So the
5
yes,
does
good.
not divide the.
Yeah. So let us take P to be 5. So 5 is a prime element in Z, no doubt. And 5 divides a0 a1 dot dot a n minus 1, a0 a1 a2 dot dot a n minus 1. So 5 divides, say, 15 10 5 5. 5 does not divide 1, right? And 5 square does not divide a0, 5. So your conclusion is, what is your conclusion then? That is important. What is your conclusion then? Fx is
It's
irreducible.
irreducible.
Fx is irreducible in qx, the quotient field of z. So qx, it is irreducible in qx. Okay, but as the polynomial is a primitive polynomial, because the coefficients are 1 15 10 5 5, and the gcd is 1, and this is a unit in z. As a result, this polynomial fx is a primitive polynomial, and hence by the result already I have mentioned, this fx is a irreducible in zx as well, because that was an property, if and only property. So as fx is a primitive polynomial in qx, fx is also an irreducible in ZX. Is the argument clear to all of you? Okay.
Sir, do you need proof of this theorem?
Sorry?
Do we need proof of the theorem?
Yes, yes. There is an interesting story with this Eigenstein criteria with my life. So I will explain it later on. But of course, you need this proof of this theorem for interview. Certainly, and you must. Okay. So another very important result that would be interesting. Okay. And you will be able to solve many of the problems by the next result. Okay. What it says, let fx equal to a0 plus a1x plus an x to the power n belongs to zx. Now this is specially for zx. Be a polynomial of degree greater than 1 if there exists a prime number. Now you can understand that we are already in Z, so I can think of prime number such that f bar of x equal to a0 class plus a1 class x plus an x to the power n belongs to zpx is irreducible in zpx, then zpx, and this is very important, degree of fx should be equal to degree of f bar x, then fx is irreducible in, again see I started with z but my conclusion is on q. So fx is irreducible in qx. What is this meaning and what is the meaning of this notations? That's very important. So suppose I start with a problem like say fx equal to x cube plus 2x plus 2. Okay, so that is in zx. Now one thing could be you can factorize it and you can say that whether this is irreducible or not, right? Since this is in zx, now you can understand that since this degree is 3, so that will be within our degree 2 or degree 3 theorem. And if you can show by some chance that there exists no root of this polynomial in z, then you are basically done. Then you will be able to say that okay, this is not, this is irreducible. But using that method it may be difficult, but using this method it is very easy. Okay, now if I consider this, and suppose if I consider like this, if I take p to be my 3, okay, we may start with p equal to 2 as well, then you will find that it may not happen. But if you take p equal to 3, then what is happening, this f bar x should be x cube plus, then this 2 becomes class 2 x plus class 2. That means they are all class 2 modulo 3, and this means class of 1 modulo 3. Okay, now this belongs to z3x. Now if I ask you the question whether this has any root within z3x or not, z3 or not, now you may not be able to factor this, but if there would be any root of this, then that root must belong to z3. And in Z3, you have only three elements: class 0, class 1, and class 2. So just put the values of x here, 0, 1, and 2, and check whether for some values of this 0, 1, and 2, f bar x vanishes. If f bar x vanishes for some of 0, 1, or 2, then you will be able to say that okay, there must be a root there. But if you find that none of this 0, 1, or 2 will make this f bar x to be 0, then what will be your conclusion? There will be no root within this Z3. So let us try to find what is f bar of 0 class. If you put f bar to be 0, then it becomes class 2. If I have f bar to be 1 bar, then it becomes 1 plus 2 plus, so our bar means class 2, and that is also not equal to 0. So that is 5 and its modulo 2. Okay. And what's about 2 bar? And that is, so this is 8 bar plus this is 2 means 4 bar, and that is also 2 bar, and this is 6 and 14, also not equal to 0 bar. Okay. Will make fx to be 0, then what would be your conclusion? That f bar x has no root in Z3. That implies f bar x has no root in Z3. Then what is your conclusion? Just have a look at this result. So this is a 3-degree polynomial. So what we have just now did, so that was for degree 3 polynomial, and it states that if it is a degree 2 or 3, then the polynomial will be irreducible if and only if, okay, it's a primitive, then I think it's somewhere else. Yes, this one. So if this is a degree 2 or 3 over a field, so Z3x is a field, then it's irreducible if and only if it has no root in f. So you can convert this whole thing into zx or even qx, and then you can conclude that. What is your conclusion? Your conclusion will be that implies fx is irreducible in where? In qx, not in zx. Mind that here the conclusion is on qx, but as the given polynomial, this is a primitive polynomial, as fx is a primitive polynomial in zx. So what would be your conclusion? Your conclusion will be fx is irreducible. fx is irreducible in fx is irreducible in zx as well. Okay. So you can use this theorem very easily by choosing x to be sorry, p to be 3. Now you can understand, you may also choose p to be 2, then you will have f bar x to be x cube, and from that x cube we won't be able to conclude anything, because x cube is a reducible polynomial, because you can make it x into x into x. So it is a reducible polynomial, so you will not have any conclusion from it. But if you take p to be 3, then of course it would be an irreducible polynomial and you are done basically. Okay. So that is very interesting and important result, and many of the time people use this result. Okay. So another interesting point is, this is sometimes this result, not very frequently, but sometimes this result is also very useful to solve many of the problems. For example, it says that let fx equal to a0 plus a1x plus an x to the power n, belongs to zx. Again, mind that it is belongs to zx. Be a polynomial, be a polynomial of degree n, and a0 not equal to 0. That means it's a non-constant primitive, non-constant polynomial of degree n. Let u by v belongs to q, be a root of fx, where GCD of uv equal to 1. Then u must divide a0. Mind that u must divide the constant term and v must divide an. Okay. So u must divide the constant term. U was in the numerator and v was in the denominator. So u must divide the constant term and v must divide the coefficient with the highest degree term. So sometimes this is very important because many cases we try to show that there exists no such rational root. Then if you use this, if possible there exists some rational root, then it will be like this, and then suddenly you find that okay, u and v must satisfy this property, and from this property you might get some of the contradiction. For example, suppose I consider fx equal to 2x cube minus 7x plus 1, and I need to check whether this is a primitive, this is irreducible or reducible in zx. Okay, so one of the ways to find basically whether it has any root or not. So since this is a 3-degree polynomial, you can very easily do that. But finding such root may be difficult, but you can also use some of the techniques. For example, you cannot use p equal to 2 here. In the last theorem we used p equal to 3, but here you cannot use p equal to 2 here, because if you are going to use p equal to 2, for example this, then it becomes, the degree will become less than 2, because this term will vanish. As a result, the degree will be of degree 1. But in that result, mind that another point was there, the degree has to be same. So both the degrees has to be same. So this is very important, both the degrees has to be same. As a result, you cannot use 2 here. Okay, but I am giving you another way of solving the same problem. So here you can use maybe p equal to 3. If you use p equal to 3, you may get some result, but here you may use this theorem. What it says that let u by v be a root, of this polynomial, be a root of fx. Then according to this definition, what is your conclusion? You must divide the a0 term, that is 1, and v must divide the highest coefficient, that is 2. Okay, so what could be the value of u? So u must divide 1, that means the value of u could be plus minus 1. And what could be the value of v? That should be plus minus 1 or plus minus 2. That implies what would be the value of u by v? The value of u by v could be, say, half, could be minus half, could be 1, or could be minus 1. Now, instead of looking at all possible values of q, you just need to check whether these values are roots of this polynomial or not. You can put these values and check whether this value becomes 0 or not. If you find that none of these values, by putting these values inside this fx, it becomes 0, then your conclusion will be this cannot be the root of this polynomial. That means there exists no polynomial, no root from q. Okay, so if you put, so you can check that fx is not equal to 0 for all x belongs to this set, plus minus half, plus minus 1. What would be your conclusion? That implies fx has no rational root. What would be then your conclusion? Since this is a degree 3 and it has no rational root, that implies fx is irreducible. Fx is irreducible over where? Qx. Okay. And if it is, since this is a primitive polynomial, implies fx is also irreducible in zx. So we are done. So this is irreducible. Okay. So that's what why this result is very important. Okay. Another result, sometimes this is being asked directly, that is what is cycloatomic polynomial. Cyclo, sorry, cycloatomic polynomial. Atomic polynomial. What is the meaning of this cycloatomic polynomial? Okay. So it is denoted by, suppose some prime is there, it is denoted by phi of x equal to 1 plus x to the power p minus 1 is irreducible in zx, where p is a prime integer. That means cycloatomic polynomial means of this form 1 plus x dot dot x to the power p minus 1. Mind that here the p must be of a prime. For example, if I have phi of x, 5 of x, that means 1 plus x square plus x cube plus x to the power 4. That is a cycloatomic polynomial in zx, and this is irreducible in zx. This is also a primitive polynomial, so this is also irreducible in Qx as well. Okay, so that result is also important. Going to, I'm sure that you are tired now. Based on these results, just try to solve 3 of these problems. Please take the screenshot of this, or you can go to the December net page. Please take a screenshot of this problem and then try to solve. The result that I have already given to you, you will find that now it's would be easy for you to solve. And remember, all these results are being that are being used in many of the problems. I have given all the results in a one single frame, so it would be very easy or convenient for you. So if you just have a look at this video for a few times, and if you just collect all these results in a particular place, then you will able to solve almost all the problems. So I think you have already taken the screenshot of this page. Then take this one, it's in 2014, and then take this one, it came in 2018. Okay, so that's the uh, it's though it's, I understand that there are too many results, yes, and it's a bit tricky to remember all of them, but write down all the results side by side with some examples, that the way that I explained, then it would be very easy for you to, convenient for you to remember all the results. And based on these results, you will be able to solve almost all the problems that appeared in NATE and GATE related to this. Almost all the problems. Few extra results are needed, but that requires more things. So when we'll do, or when we'll able to solve more problems, then you will encounter with those properties. Okay. So any question or comments that if you have, please let me know.
Sir, you are saying about ZP. Is it always easy to find those kind of P? Because we have to certainly guess those things
So
before
in
doing.
competitive exam, once I have seen, it's up to, I think it's up to 7. So 3,
Okay.
5, and then 7. So usually for 2 and 3 it works for competitive exams. But in 1 year I have seen it came for 7. Yes, that would be a little tricky, or you need to do more calculations. But theoretically, that can be done. Yeah. I mean, those who are giving the problem should have some mind, right? They cannot give you 101 to check. So if this kind of problem comes, it's better to leave that problem, because there are plenty of other problems waiting for you. So I am dealing with this kind of competitive exams for more than 21 years. So I know that it's not really that you will able to do each and every problem. So if you find that you are not being able to solve due to this calculation, it's better to leave. There might be two things: either there might be some tricks that will help you to solve that at that time you couldn't find that trick, or there might be the question is itself quite lengthy, you have no other choice to do this calculation. Then it's better to leave that problem for the competitive exam, because many other problems are waiting for you.